In the mid-littoral zone, parallel vegetational belts are more developed. Eroding cyanobacteria, patelaceous gastropods, limpets, and chitons are more abundant. They all contribute to the erosion of the underlying rock by grazing the vegetational belts, and in sites sheltered from strong wave action, they enable the development of a reclined U-shaped or V-shaped intertidal notch. The vertex of the developed tidal notch is located near mean sea level, the base near the lowest tide level, and the roof near the highest tide level. The bioerosion rate is generally maximum near mean sea level and gradually decreases towards the upper and lower limits of the intertidal range. The profile of a tidal notch is an excellent sea level indicator because it provides information on the duration in which mean sea level remained at the level of the notch vertex. Fossil tidal notches in submerged positions have often been used to deduce former sea level stands and tectonic movements. In particular, the good preservation of a tidal notch profile after its submergence may be used as excellent evidence to determine whether the subsidence was rapid, possibly coseismic. Microerosion measurements have shown that the deepening rate of a tidal notch profile may be very variable since it ranges from less than 0.1 mm per year to more than 1 mm per year, with averages of the order of 0.2 to 0.3 mm per year in some sites of the Mediterranean. This high variability may depend on seasonal changes in the environment, temperature, salinity, air pressure, that influence not only the intertidal vegetation and grazing organisms, but also the sea level changes over seasonal or interannual scales. In spite of this variability, the inward depth of fossil notches may be used as an approximate method to roughly estimate the duration of a period of relative sea level stability. All carbonate rocks are not equally sensitive to tidal surface, may locally prevent the development of a tidal notch. During the last 2 centuries, tide gauges have shown that the global sea level was rising at a rate faster than the possibilities of bioerosion. As a consequence, new tidal notches have not been forming in most places during the last couple of centuries. There are various tidal notch profiles for submerged notches, resulting from different combinations of relative sea level in sheltered areas. Tidal notch profiles under different conditions on a vertical carbonate cliff from different combinations of relative sea level changes have been distinguished and allowed to qualitatively discriminate the way of subsidence, for example coseismic event, gradual relative sea level rise, etc. Reclined U-shaped notch profile. The height of the notch roof, HR, is very similar to the height of the notch floor, HF. A rapid subsidence movement, for example greater than the tidal range, resulted to an underwater preserved former notch. Here you see an example of a continuous submerged notch of type A submerged notch in Casos Island. Two submerged former notches which were preserved after 2 rapid subsidence movements greater than the tidal range. Here 2 submerged notches in Carpathos Island are depicted. The lower one is of type B profile. A rapid subsidence, smaller than the tidal range, preceded and followed by a millennium of relative sea level stability, produces a notch higher than the tidal range. Two vertices appear, separated by an undulation in the notch profile, indicating the former and the following mean sea level positions. Here you may see an example of a submerged notch of type C in Karpathos Island. A gradual relative sea level rise at a rate smaller than the bioerosion rate produces a notch profile much higher than the tidal range but of limited depth. Here you may see an example of a submerged notch of type D in Karpathos Island. In the case of a gradual relative sea level rise during 1 millennium, followed by relative sea level stability, the notch height becomes greater than the tidal range, with the height of the notch roof smaller than the height of the notch floor. Here you may see an example of a submerged notch of type E, variation 1, from North Corinth Gulf. In the case of relative sea level stability, followed by a gradual relative sea level rise, the notch height becomes greater than the tidal range, with the height of the notch floor smaller than the height of the notch roof. Here you may see an example of a submerged notch of type E, variation 2, from Karpathos Island. A rapid subsidence movement resulted in a submerged former notch. The following continuous recent sea level rise has resulted in the absence of a present-day notch, but a kind of visor just above the water surface is produced by dissolution in areas where fresh water flows. Fresh water, coming from underwater springs, tends to float at the surface of seawater, dissolves the limestone rock, contributing to the production of upper intertidal undercuts. For certain cliff profiles, where the limestone rock tends to protrude above the waterline, a kind of visor just above the water surface is produced, especially where a tidal notch is not present. Such a visor, that might resemble to a tidal notch, for which only the roof is preserved and the base is missing, can be found alone, or above a submerged notch, and should not be confused with a tidal notch. This submerged notch, of type F, is from North Corinth Gulf.